Thank you to be here for the lecture of today. Today, we go ahead with the discretization of the discrete controller. And let me restart very quickly to recap what we did last time. But I forgot to, because we need this. No? Just a second, because I forgot to install stuff. Ready. This is ready. This is ready. Excuse me for this interruption. Okay, should come. Let me. Yeah. As I told you, a little bit funny if you look if you look at the videos. But anyway, if can help, for me, no problem. Okay. Very shortly, we started speaking that basically you have two methods, or better to say two methods is not correct. Two possible main streaming in the methods. One is the emulation method or the methods, because also inside this technique, let me say we have also variation. And another one, the name is direct method. Let me reconsider very quickly the emulation method or the methods. Uh, just saying very quickly that the idea, the basic idea, um, is to design the controller in continuous form, as we did in dynamical system, as we did in automation. In automation, we consider just a linear system, and I don't remember if at that time and then in this semester I introduced also the linearization, but I will tell you uh, in the next lecture. But in any case, assuming that we are able to design um, a controller in continuous form. Look here. This is the controller and a PI controller in continuous form, in which the coefficient of the proportional coefficient Kp and the integral coefficient is Kp divided Ti. To design the parameter to design are Kp and Ki. No? This means, in this sense, Kp and Ti. We can see here. Once we are able somehow, with method which we have seen in the previous course, to design the controller. This means at the end, using the simulation to validate at the end the performance of the controller, and assuming that we are satisfied, we try to realize the discretization of this system here. This is the name, this idea, let me say, justify the name emulation. I don't know in German, emulation, emulation. It's the same meaning. This is, we try to track, we try to follow, we try to imitate. Imitation. It's correct also in German.
Yeah.
Emulation, maintain the same meaning in Latin. Latin means follow, but more follow we have them in frame, and we try to be similar to this, to follow, to. Okay. And interesting, this last sentence, you remember last time, this means that after the discretization of the controller, because in the microcontroller, when we use the microcontroller, everything is discrete. Even though sometimes it seems that we, also in MATLAB, also last time, we implemented continuous, but the microcontroller and the MATLAB automatically inside its structure will sample the controller. But of course, we can do directly without leaving this task to MATLAB and directly, I mean, to approximate this. And then, of course, we can change parameters. We can, let me say, fix the sample time and so on. Otherwise, we give this task to MATLAB. But in any case, it's better if we do directly because we know what we do. Otherwise, MATLAB does something. Of course, we can know what MATLAB does because if you look, there is a setting. There is setting in the MATLAB in which you can see which kind of method is used to discretize. You can look. Anyway, there are options. Also in MATLAB, and we can of course look at what MATLAB does, but exactly what it does is not so easy to. We have to look in the program. Okay, look here. We hope after this, we hope very important this sentence, which it seems to be does not belong to the scientific field, but now I clarify the meaning. That the properties of our original continuous control system are preserved. Why that? Because as I told you last time, any kind of discretization is an approximation, not only of a signal, but also the dynamics itself is an approximation. I don't know if you remember in the course which I started from a linear, linear or non-linear continuous model. The discretization of the model is totally different. I mean, first of all, depend of TS. Secondly, the dynamics change depending of the method which I use. Forward Euler or backward Euler or in Runge-Kutta with different variations and so on. This means the dynamic itself is not only, let me say, depending of the S, depend of the methods. This means really we can change totally the dynamics. We can see here, for instance, that the signal is approximated, but this is not the real problem in our context. Why that? Because it seems clear from here that if Ts is smaller, do you remember last time, we have a better approximation of the signal. Why not? If you consider a very large sample time, from here to here, I don't have information about the, let me say, real signal or the continuous signal. If I reduce the sample time, it seems to be that I approximate better the signal. But in the context of an approximation of dynamics, I don't know if you remember in dynamical system, in other courses, we cannot choose T as small as we want because we lose the controllability, we lose the observability. I don't know if you remember this in model predictive control, for instance. But anyway, I will come back on this later. Okay, let me go ahead quickly. This is the system which I want to do the discretization, excuse me. And of course, we hope after the discretization, the stability in particular, but also dynamics, its robustness are preserved. Preserved means that remains, more or less. But of course, we can understand very well that it could happen that always the performance will be deteriorate. We lose something in any case because we approximate the signals, but more than the signal, of course, also the signal, more than the signal, the problem is the dynamics, which this is not reflects the original dynamics which we want, which we designed, which we tested with MATLAB, and we were, let me say, satisfied, assuming that we were satisfied. Otherwise, we cannot proceed with the discretization. Laplace transform of this expression here, and look, in order to, that at this moment, I don't use directly, but we will see later that can help us also this expression here. Using forward Euler, we will see a little bit the idea which I told you also last time to approximate the PI control. I start with the PI control in order to be more concrete. We can use whatever kind of controller, but why that? Because we know from dynamical systems, we know from automation, not only, therefore, is one of the most used, one of the most effective in each control conference, which is a track. PID control, always, because it seems to be easy, but it's not. Look here. Something recall as and PD, in this case, controller. Look, in this seminars, the rest of the seminars, I will tell you about also different methods. What is written here is basically the approximation of an integral. The integral is the most important, most important. I don't want to say the most important, but the most critical element to be approximated. Let me clarify this in the next sentences. Um, I recall the states, the integral state with Q, as in the literature very often is Q is not X, but in our lecture, do you remember Xi is this augmented state of the integral? Here is still an continuous, let me say, integral from 0 until k multiply t. K multiply t is our, let me say, t is our t not capitalized. No? Is our t not capitalized. Now, to approximate this expression here, as in high school, we consider the sum. We consider the sum between 0 and k minus 1. Do you remember last time I tried to explain? We have basically k elements, and this basically is the approximation of, do you remember last time, of the surface which I have. Let me go ahead quickly now because I already, which I have under the function e. No? The integral, you remember in high school, the integral can be represented as the surface of the, in high school, we know that. Yes. Yeah, and now let me spring here because basically it's the same. We can understand better this expression with the sum. First of all, to be clarified, you remember last time I told you why k minus 1, if here is k. Yeah, because if you look at this picture here, we can understand very well that, let me consider, let me take something to indicate. Yeah, right. Yeah. The surface is quite clear, as, as let me say here, expressed. No? This is the uh, surface at time k, and this is the surface at time, let me say, k plus 1, if you like. And we can see that is this red surface is a calculated kt, this level, multiply t or the ts, no? Typically we consider t or ts the sample time. We can understand now very well why I need just, oh, it's written here k minus 1. The reason is that to take basically this surface here, we need this element here, uh, which is this amplitude, multiply this this interval. But this element here is the element before of this one. Here the notation is not k and k minus 1, but it's k and k plus 1. This means at this point here, I can calculate this surface, this red surface. Therefore, I will consider in A of kt. If I want to calculate the surface at time t, which multiply k plus 1. We can see here, no? The surface calculated t, which multiply parenthesis k plus 1 parenthesis, is the surface at, let me say, calculated at time, let me say here 0, because this amplitude multiply this, which I already, let me say, calculated, plus the surface, which I will calculate at this time here, for the surface, which includes both. Exactly. Let me go ahead here quickly now. It's a quick repetition. Before, nevertheless, go ahead, we stopped last time here. I would like to repeat the concept of shift or shifting, if you want. Again, for sake of notation, typically in each book we consider this. This means you can neglect in the argument the sample time, no? As if it's always there, but we don't write this because typically it's constant, but it's not necessarily constant. Here, you can image t, even though to simplify the notation, and you can find also in the book this notation here. Very important. The operator Z is in a complex operator. At the end, we will see that is connected with the zeta transform, zeta transformation. Now, I would like to introduce this concept of the variable set as an operator and a shifting operator. We can see here that we define this element here in this form here. Z multiply x of k. Think about x of k multiply t, but t is there always in the argument. We didn't put just for the notation, but it's there. When you program with MATLAB, we have to consider this t, but it's easy to do. This is a shifting operator because z multiply xk equal x of k minus 1. This means is in a shift forward of the element. Of course, a little bit strange in a shift forward because if I have a time x of k, this means this is in the form of a prediction. In fact, very often we write in this form here, which is the equivalent as a delay block, as a delay element. Z up to minus 1 multiply x of k is x of k minus 1. This is more physical because I know the past, but I don't know the future. In fact, you remember, Vincent, in the model predictive control, we try to approximate or to predict the future using a model. We do also the same in our life. No?
I love this.
Yeah, we do also the same in our life. Now, if the model is not good, or let me say, also in the life, it depends of our model of the life. This means our vision, our principle, our past. We build a model with our past experiences. We can be for the future more pessimist or more optimist, more conservative. This is basically what we do sometimes in some project here. In the mathematical psychology, I told you that we have some projects in mathematical psychology, in also some diseases as I told you, as bipolar disease.
Yes, I remember.
High, down, this is sinus, cosine.
He was talking about
Exactly.
Yes.
Yeah, you can see here.
Yes. And the problem there was it's very hard to predict. how the behavior will be in the future with the bipolar people, right?
Yeah, yeah.
But then
Two
you said
patients.
we can't extend T, like we lose of the observability. But you mentioned to him.
No, when it's short. When it's too short,
Yeah.
we lose the observability, we lose the controllability. When it's too large, we have nevertheless the problem Shannon theorem, but basically means is more is the problem of the signal. Because something happens, but for our representation, nothing happens. Because from here to here, I have this information. From here to here, we remain with this information. But in the meantime, the signal is going ahead. It could happen that we have something like that. This means, of course, roughly speaking, cannot work. Mathematically, there is also theorems to formalize why it doesn't work, but intuitively it's clear. I mean, if you want to get an information of a very fast signal, you need to sample very fast, much faster than the phenomenon. In the photograph, I don't know if you know a little bit the photograph technique. If you want to shoot in a car, this is running really fast. You have to program as the opening time, which is our sample time, very short. Otherwise, you don't see the phenomenon.
The lens is too slow.
I am not expert, but something like that.
Well, yeah, good comparison.
Something, I'm not expert. I don't have the camera. I mean, now everybody has the camera in the handy, no? But I'm not expert on this. A question you want to important to understand. It seems to be. It is true. Statically, I can consider very short TS and then a good representation of the signal. This is valid. But in our structure, we don't have just the signal, we have the model. I hope that I show you. Otherwise, I have an example for other courses. And the model, it's a shame, is exactly the contrary. Very short TS, we lose the dynamics. I show you, probably I have also here, of course. About this shifting is clear. At this moment, it's not just a mathematical operator. Physically make more sense, this. But also this one in the sense of possible prediction. But anyway, it's too abstract physically, this, because the prediction we do with the model here, we didn't introduce any model. This means this is the typical notation we will use starting from now. But mathematically, I can define what I want. Last time, we conclude here. Yeah. About the approximation of the surface, I told you a little bit, probably a little bit too faster, but I don't have now time to go in depth, but it's intuitive. Very important to understand why I am considering k-1 as not k, because the surface can be calculated starting from here, because t is fixed. Yeah, again, q of kt is the old area because I am imagining to be here, just as in a photograph at this moment. Don't think about the dynamics. It's in the signal. I can now, using the shift, to characterize my PI, my PI. Look here. This is the approximation of the P, no problems. This means KP multiply A calculated at KT, KT I put, let me say, I throw away, but it's there. Look how I realize the integral. Here is the old, let me say, surface, which is updated. So basically, at the next step, I have a q k plus 1, which is this one, equals the old plus this new part. Basically, I copy it here. This means the output of the controller at time k is kp multiply the value of the error plus 1 divided ti multiply Q at time K and updated the input, I will consider this, no? Because I accumulate. It's something like that. I accumulate the surface. This is the surface which I can calculate basically from here. But of course, at time K plus 1, as I told you, multiply T. I don't know if this is the yeah, is the U of K, which is updated in this particular form. If I want to calculate U of K plus 1, here I have a K plus 1 because here we don't have dynamics, but here we have a dynamics, which is characterized by the integral. Q of K plus 1 is this one, the old plus the new. Everything is known. Now we can see here. Here I introduce this shifting. I don't know if you remember the definition. I can consider Q of K plus 1, Z multiply Q of K, no? As I told you about the definition. Quite abstract, quite mathematically. We will see a little bit the meaning of this Z. Here I don't have to change anything because it's a time K. This could be represented in this form, just applying the definition without thinking about the meaning. Let me go ahead with the meaning because we will see now some interesting parts. I copy for you, or better to say, this part here, but I copy for you this part, and I put, look, it's an easy calculation. I put on the left part this one. I don't know if from here to here is clear. If you subtract right and left and right, Q of K, we can see here, and then I put in evidence Q of K, I think is clear, no? From here to here. This expression is equivalent to this one. What is the idea? The idea is to find an expression, which is an expression, a transfer function, in terms of Z. This is the idea. And then we will see something, I would like to say, more interesting, even though the transfer function itself, if you remember in automation, is quite abstract because it's based on a complex function, a complex variable is a complex function, S. No? The variable is a little bit not so easy to interpret. Now we have, because from this second equation, we can obtain the transfer function between here, the integral and R. Q of K divided A of K, transfer function between the integral of the R, or in some literature, the R is the integral, is T divided Z minus 1. We can now consider this expression in the equation 1 to obtain at the end the transfer function between error and output of the controller. So we can somehow abstractly, we are able to characterize the controller in discrete form using a transfer function, a pseudo transfer function. Instead of S, we have a Z with a shifting operator. If you remember in MATLAB, we have the block Z up to -1 or 1 divided Z. Is this?
Yes.
Is this one?
Oh,
Delay. The name is delay. If you want, I show you.
I know this one.
It's exactly this. In fact, when we realize the model in discrete form, we use this 1 divided Z. Sometimes we use also for different goal, no? In Kalman filter and so on, but it's in a delay. Using this, which is in a transfer function, but plugging it here, we can obtain easily, let me go a little bit faster, the transfer function between error and output of the controller, or vice versa. In the book, you can find also between U and E. It depends if you read the transfer function as the input to output, or if you read mathematically numerator over denominator, no? On the yeah. But in any case, the transfer function is we can see this in a function of z. This means we have an analogy, and I will bring this analogy at the end of the seminars. And you agreed we do a little bit lecture also in February.
Yep.
And then, of course, parallelly, we can meet for the project. This is the sense of the seminar. Otherwise, we don't have an examination in the classical sense. No? It's the project. It should be nice if we obtain publications, something like that. But it's not necessarily to obtain 1,0. No?
Depending.
Nah, nah. At this moment, we didn't obtain any publications. No? But we had nevertheless 1,0.
Yes.
Nils, also for you, no? Without publication, this means it's not a necessary condition. Of course, it's sufficient. If you have, no, it's clear. No? Why I have to pretend as a necessary condition to have 1,0, then it's not written. But of course, if you have, it's clear what I have to say. I remember once, just shortly, we had in the commission with Maren, and in the master thesis, and I had doubts as a student of mine, and Maren was the second supervisor. Um, I told Maren, I said, I'm not sure, I have a doubt between 1,0 and 1,3 because, but anyway, I put my motivations, my reasons why that. And Maren told me, but he had 2 publications. Nobody have to have publication. I don't admire my, I don't have doubts. In order to understand, of course, if we have something which is interesting also for the community, why internally we have to have doubts? Anyway, if something is not clear, or but it was done more than required or not. I mean, it's not required to do publications. I mean, a referred publication. I don't speak about the publication of something which you put in your private repository. I have a homepage. I publish what I want, more or less.
Yes.
But it's in the referred conference, in the sense. Okay. Look, please pay attention now. If you compare the continuous controller with this discrete one, then look interesting now. Now I'll show you why at the beginning I told you I calculated the transfer function I will use later. You remember I told you. Because I have this expression as in the transfer function, or in general, u of k as in a function of e of k is this one. If you compare with this expression, you can see, look,
Minus y.
one is the same.
Yes.
Ti is the same. Did you agree?
Yes.
If S equal, let me write equal, and then we will discuss circa. T, let me say k minus 1 divided t, because is in the denominator. You have to divide by t. It is S. Why I put circa? Because we are speaking about in discretization. This means everything is built with this assumption. This means now is a little bit very fast this explanation, but makes sense. The assumption is we approximate. This means we cannot say that this UK is exactly UT. But if S is circa this, we can say exactly But now from here, we can see interesting thing. From here directly, that very small t bring problems. Independent observability, controllability. If t is very small, I cannot theoretically infinite small. Of course, as we cannot divide it by zero mathematically, but also we cannot consider the denominator very small. That we have some problems. Because this is not yet clear what this is. Because this could be also very small, but if z is close to 1, but let me more roughly. Can be seen better probably from here. Look at this comment here.
This approach works for t smaller than...
But not too small. Of course, this isn't a feeling. What is the meaning too small? In fact, I put to be interpreted. This means also in German. Einführung, this means we have to interpret what is too small. But you can see here. Now here, physically, is more clear than here because we cannot divide it by zero. It's a mathematical sentence. We learned in high school, in elementary school. Do you remember? We cannot divide it by zero as the definition. But then in high school, we learned if the numerator is nevertheless also close to zero, it's then clear. Now we can, do you remember the concept of the limit? Something zero in the denominator, but if something more or less zero with the same rate of the denominator, it could be more possible limit, but just to understand what we are doing. This means here is more mathematically, but here we can understand now what I told you about the controllability, for instance. The observability is not yet visible. I will tell you in February. But we can see that for t very small, t is this here. The system is not controllable in the sense that I will destroy it, at least the integral part. I mean, we have this uk is k multiply e of k. If t is small enough or very small, I will destroy at least, in this case, I will destroy the integral component. This means, of course, if I start with an PI because I need a PI, because in accordance with our methods, we have seen that the PI works, including the E part, and then I say, but please, we can see that the representation of a signal is very, very, very good considering very small sample time. If I do very small sample time, my original PI collapses in IP. This could not necessarily works because if I need, if I certify that my best control is an PI, now if I consider T or T very small, I collapse in just one P. This means it could be that doesn't work. It could be that the controllability now is not so as I want or as I wanted. I don't know if it's clear this.
Yeah, I think so.
This is the controller, which reflects or approximates the continuous controller. Nils, Lauri. And then I say, but look, probably it's better to reduce the t, so I have a better representation of the signals. Please pay attention, we have in controller signals, and dynamics of the controller. It's as in each system, we have the structure of the system. In fact, do you remember, we have the block of our system, GS or differential equation, and the input signal. You have two things to obtain the output. The system and what I apply the system. Now, to represent the system in the best way, it seems that TS should be very small. This representation does not depend on the system. I didn't tell you.
But I think it makes sense because when you think about integrals, the more integrals you have to represent the area, so it's getting more defined, right? So that's representative of the
right. Areas. But you are considering just the signal.
Yes.
When you explain me this concept, you didn't introduce system.
Mhm.
Just to have an abstract function, and you want to approximate in the best way the surface
Mhm.
under the integral or in the upper part, backward, I will tell you now.
Yeah.
But in our concept, we have something more because we have a dynamics. This means you have a signal, but the signal is go inside a system. Now, if I represent the system in discrete form, and in particular the controller, we will see for the system a little bit different. But if the system is useful for the controller, Vincent, you understand very well because in model predictive control, we use the model in the controller.
Yeah.
This means we have to discretize the model. But remain on this lecture for Niels and Laurin. The controller must be represented, must be. Now I do a PhD program with Manuel, you know Manuel Schumacher, and we do a PhD in analog systems. We forget everything in what is written in the microcontroller. We are using operational amplifier, operational amplifier.
Yeah.
In this case, we don't have this kind of problem. The operational amplifier controller is the best.
Mhm.
But the problem is drift. I don't know now if there is new generation of operational which is avoid this drift, you know, that is, they change the characteristic because of the temperature or something like that. I'm not expert, but
Mhm.
because the digital controller, the discrete controller is really worst.
Yes.
Yeah, but what is why they apply? Because we can change the characteristic, we can program it very easily with MATLAB. Otherwise, you have to build harder.
Yes.
If you change the dynamics and the resistance, the capacitance, you have to put in this board new components. You know?
Mhm.
Here we have a representation more abstract. Um, yeah, in order to generate my output, which is in the controller, is something different. We have an input error and here u of k, or u of t in continuous. This is nevertheless in our normal application, in manual application, no, in the microcontroller. This means the example which I put make full sense. But of course, also the model, if the model plays a role in the controller, model predictive control must be considered in discrete form because it's part of the controller.
Mhm.
I don't know if it's clear. It's important to analyze this in terms of controller because the controller, in MATLAB, everything which we have here, is not analog, it's discrete. Okay, let me a little bit go ahead. If I have a controller in which we are satisfied, with the performances, I can approximate the controller, the transfer function of the controller, putting S equals Z minus 1 divided T. This approach, the name is emulation, came from this consideration, from a practical example, of course, which is PI, but I consider this example because you know no, the PI. From here at the end, what is the conclusion? The conclusion is starting from this system here, continuous.
Mhm.
If I put S equal T divided Z minus, and I will obtain this. This means at the end, this could be a recipe of Deutsch Rezept.
Yeah.
And now with the model with the PID which we have in our project, we can directly try to do this.
Yeah.
Yeah, exactly. It could be, but I would like to go a little bit ahead. In any case, I have this example in my data, but probably could be to speed up because It's extremely easy to do. I can send you the file if you want. Basically, I have this process PS 1 divided S square, and I controlled the system with this controller, which is in a PI controller. No, it's in a PD controller. No, it's exactly the integral derivative. Yeah. Ah,
Mm.
it's in a P. It's in a PI. If you uh, consider S divided this basically a little bit more complex and a little like without this is a I have to do the calculation. Let me go ahead. Everything in control. Everything in control. Now, if you apply the method S equal Z minus 1 divided T, we can approximate, Z is approximated CS, it is this expression here. Just doing the calculations. Then I put just to check T equal 1, but this must be verified. No? This must be verified. We have this form of the controller. Let me see. Applying this method here, we have this controller here. For T equal 1, this is basically is the transfer function which I have. Apply the transfer function uk divided E of k consists of this expression. I can write in this form here, just multiply by Z left and right, just multiply left and right by E of k. At the end of my calculation, I have the control law. uk has this expression. This can be implemented. I have also in MATLAB, if you want, I can look if I find quickly. And this controller here approximate bad or not bad, depends of T. Of course, here just to simplify the calculation, I put T equal 1 in order to show the methods. But of course, it could be that I need T much smaller. I don't know if it's clear. Our U should be calculated using this expression here, U of T. U of k, in some sense, is easy to be calculated because what is the meaning of this? U of k, if T is equal 1, probably I have, okay. I put here the general expression with T without putting T equal 1. Here, just to simplify the calculation, which I say for T equal 1, U of k is 3 times E of k minus 2 times E of k minus 1, the previous value of the error. Everything divided by 5. And then I put here the general expression for any T. This means I don't put here T equal 1. Do you remember T equal 1? Was this here, no? I put 1 here, I put 1 here. If you don't put T equal 1, we have a general expression. Believe me, the calculations are quite boring. But look, at the end, we have this expression. For any kind, any T in this sense. No? This is the general expression. For T equal 1, we collapses in the expression which I already told you, expression 1. Please pay attention here. This is quite interesting in this case. For T equals 0, for t equal, in this particular case, for t equals 0, look, we have uk equal uk minus 1 for each k. For t equals 0, for t equal 1, we collapse this in this. Very interesting, for t equals 0, this means very small practically. T equals 0 cannot realize the quantum, but 10 of minus 6, a microsecond, 10 of minus, look, we destroyed the controller. Do you remember at the beginning I told you for t very small, we lose the controllability. This is the meaning. If the output of the controller at each time, at each k, does not change, yes, of course, for t equals 0, we cannot control. Because the concept of the controller change the output depending what happens. Here, independently of what happens. For t mathematically equals 0, the controller is diet. Of course, t equals 0 then makes sense. We have a t up to minus 7, 0,1 microsecond. The reaction is very small because we tend to a constant output of the controller for each t, independently what happens. This is the meaning of these calculations. It's clear, no, Vincent? Independent of what happens, because it's this is what results, or we tend to the situation if t tends to 0, if t is too small. We can see that the controller doesn't work. Therefore, I told you at the beginning, we lose the controllability without introducing the concept of the controllability, but the controllability, the reflect of the controllability that the controller is on life. But if UK, circa UK minus 1, of course, the controller does not react. If this is just a mathematical condition, practically means circa UK minus 1. At each time, independently what happens. Of course, the controller is not safe. Okay. Therefore, no, do you remember this sentence? But not too small. Now we can understand a little bit better this feeling. No, it's just a feeling. What does it mean too small? As means, but now we understand. I would like to proceed without showing you this example I have in Simulink. Go ahead. Probably if I find at the end of next week, let me put material here now. It's easy to show you. If I find, should be nice. Let me, are you tired? Let me at least go ahead here. It could be the last minutes. Yeah, very, to conclude this part. Look, as I told you about it, cannot be too small. We discussed a lot. Now, too small is clear, cannot be. But we can see cannot be too large. In the complementary, I told you about the Shannon theorem in sufficient condition, which states an upper bound of t. I don't want to go in there because Vincent, you heard about the Shannon theorem in my courses.
Yes.
It's already known, but we can consider we have a lower bound, not so small, but not so large. I already told you exactly now. It means probably we have an optimal t in the middle. When we have something like that, we can think about an optimal t. It is. But to calculate an optimal t is a very hard problem. But Vincent, you know Kalmar filter. You can think about to consider this t as a possible variable to be estimated. But you can believe me, it's not so easy because t is directly, but we can try. We have different approaches because this recalls an optimal problem. Not too big, not too small. We take the mean value. Recall in this formulation that it is that you have an optimal t which optimize something. When I speak about optimization, we have to understand what we want to optimize. Otherwise, no meaning for the optimization. We have to fix the cost function. And then, for instance, the controllability or the error, it could be an interesting problem, nevertheless, also for this project. But probably, in this sense, probably for you in your inside, because Kalman filter is not known, no? But we can also use a different method, PSO. Anyway, it's a possible optimization problem. You can understand, it seems at least. No? When you say not too small, not too big, where is? Okay, let me go ahead. Again, for the Shannon theorem, you know, Fm is the maximal frequency which I want to represent, in which with which I want to work, and so on. Now, yeah, look at this. This general expression is an expression in time. Our time is k, no? Encounter. K is always the argument, better to say, the argument of each function is everything multiplied by t, no? K minus 1, everything by t, but we don't put it. We want to go ahead. Look at the transfer function now. In terms of this pseudo variable set, shifting at this moment. Look, this is my general expression for valid for each t. Look now, I used the shifting operator. Instead of u of k minus 1, I will write set of minus 1 multiply u of k in accordance with the mathematical definition. Don't think about it. I put this sentence as a valid sentence, and everywhere where we have uk minus 1 or any kind of signal, also e of k minus 1, I will put set of minus 1 multiply this variable. This means instead of u of k minus 1, I will write set of up to minus 1 multiply u of k. And also here. In accordance with the identity which I fix as a possible definition. I assume there exists a way to realize this, but now we have really something concrete. Think about the MATLAB, no? In Kalman filter or in the discrete model in the complementary. If you need a delay to obtain a signal delayed, we put 1 divided z. 1 divided z is set up to minus 1. I can write here in the same way 1 divided z in accordance with the MATLAB notation. This is a practical example in which we put an initial condition, and then is the signal delayed, and inside 1 divided z, if you remember, if you want, I show you, we have to fix the delay time, our t. Could be that we go ahead at 10 minutes, then the last 5 minutes. We can go ahead with 12, yeah, or we have a lecture. You have a lecture. On 12, okay. We will stop a little bit earlier. But at the end, it could be that I look for the file in order to show you again some aspects in MATLAB, showing you this example here. I have it somewhere. Now, once we replace this with easy calculation as before, you remember we want to calculate the transfer function. This means on the left part, we have to consider everything which depends on uk. On the right part, we have to consider everything which depends on e of k. Do you remember this separation in order to calculate the transfer function? This means I put on the left part this with the minus, and believe me, this will be on the left part with the minus. Believe me, I will obtain this. We can see that I change here the direction. Instead of 1 minus t, I have a t minus 1. Algebra this. No? The idea is to calculate the transfer function. This means u of k divided e of k. This means I have to isolate on the left the contribution of u. I have to isolate on the right the contribution of e. Here is extremely easy because it's enough to bring, let me say, bring this part, this element on the left part, but I have to change the sign. Is here, no? T minus 1. And then I put in evidence. Clear, no? What should I do? This is algebra from gymnasium, probably. And then I divide it. We can see that I can divide at the beginning everything by this part. I will have this one. If you want the the transfer function, of course, I have to divide UK divided EOK, but the transfer function is this one. For t equal 1, I can have some expression, but let me consider this general, this general expression. As you see here, we can be seen instead of z minus 1, that for us, at more physical sense, in mathematical form, in this form here, in which we can see that if you consider the transfer function, this part here, basically UK divided UK, that we have a numerator and we have a denominator, as in S. We had also before, even though I didn't emphasize, poles and zero characterize the dynamics of the discrete controller. We can see a denominator and numerator. We had also before, I didn't emphasize, now a little bit more. This is the idea. I can design the controller considering where I will place the poles of the solution of the denominator and where I place the zero. Look, this depends of t. This means the choice of t change the dynamics of the whole control loop, because the control is in the control loop. Therefore, before I told you, it's clear that in a more general frame, we can consider an optimal T which influences the dynamics of the whole controlled system. This could be an interesting project, probably more for you, Vincent, that you are already at the end of the master, not you have seen many complementary, and this we will do something different, no, a little bit, because here, if you want to apply the Kalman filter or the optimization method, you attended also the class in optimization methods, but also with PSO we can think about. But the goal of this slide here is clear now. We introduce the optimization about the not so small, not so large, in the middle. Or I don't know where we have a good solution, bro. Why it is not in the middle? Because it depends on the dynamics. It's more complex, the system. But we can see here, if you remember automation, in which the poles of the denominator reflects directly the dynamics, in particular the stability. The zero also plays a role in the dynamics and so on. Here is the same. We have poles and we have zeros. We have the numerator and denominator. This means in the design in particular, until now, the sample time plays a role in the design sample time. Okay. Let me go ahead because let me introduce new concept. 5 minutes, and then the rest 5 minutes, I try to find the file. So we relax. What time do you want to go? You can say here. We don't disturb. You don't disturb us. But meet Vincent. You have to speak. But if you want, you can go in my office. I can open.
It is not online today.
In the present. This means you have to go. What time?
No,
I'll tell you. This, do you have time?
no.
Okay. We go ahead a little bit. Then, in the meantime, when I try to find the simulations, some of you, I would like to ask if you go to do a coffee, tea as last time, no? May I ask? I have time to look for the. But let me go ahead a little bit. Do you want to drink a coffee, Vincent? Yeah. Or tea. It is possible. If somebody asks, say, Paolo give us the permission. Last time worked, no?
Didn't work so well.
Why?
With
Andreas.
It wasn't Andreas, it was Detlef, I think.
But
He said he bought the coffee, so we can't have coffee.
Okay,
Oh,
tea.
even if we said that.
Okay,
you-
tea, I bought the tea. This means no problem. But I think how much can cost?
Depending on what you buy.
But we also bought 1 cup of coffee and filter coffee.
Oh, filter coffee?
Yes, not so expensive.
Okay, no, filter coffee, no. But coffee beans can be very expensive.
Let me go ahead a little bit because I would like to emphasize the difference between forward and backward.
I saw something right now dependent on that. What is Tustin method?
Yeah, I tell you now.
Yes?
It is included in the discourse.
Okay, but I need to go.
Yeah.
Toilet.
Forward, backward, Euler. Or we want, probably it's better to take a rest. We wait for Vincent. Let me stop the. I need now to introduce the backward in order to look at different, also more advanced approximations. We worked very often with backward. We have a project with Rolls Royce. I don't know if I show you with the paper, which we applied instead of forward Euler in the Kalman filter, the backward Euler, for different reasons. And basically, we have a different structure of the Kalman filter. Because as I told you now, the discretization is an extremely important part of the, we have seen today, of the controller, but you can imagine also of the observer, because an observer is in a controlled system. We have a feedback in the observer. You remember, Vincent? This means it's also a controlled system. We have seen that the sample time, t, plays a fundamental role. And this means also the method which I use to approximate or to describe the model is extremely important in the controller and in the observer. Okay, let me speak about the backward Euler. As I told you, excuse me if it's a little bit boring here, but the course is the seminar is concentrated on discrete. Therefore, we have this method to be clarified, and then we will see MATLAB and Simulink together. Therefore, I would like to show you something also today if I find. Otherwise, next week. Yeah. Very often we say that the backward Euler is an implicit method and the forward Euler is an explicit one. They are two different approaches which generate really different results. Already implicit, explicit. If you think about the word, I don't know in German, but the Latin, they are opposite.
Yes.
Totally opposite. We can see also this opposition is reflected also in math. Therefore, the words. But the word is related to another concept I show you now. But also in German means please be not so be explicit, clear. What is explicit then? Yeah, direct. Clear what you want to say. Say explicit.
Yeah, I think so. Kind of.
This implies, after that's implicit, this means
it's more of a derivative of what.
Yeah, this is not clear, but it seems that you want to say so, or generate something so. Yeah, it is something like that also here. But we can consider, roughly speaking, I mean, not a linguistic, but something opposite. No? We say implicit because we generate, this is the mathematical reason, an expression, u in particular case, because we are considering the controller, u of k, which depends of u of k itself. I show you the mathematical expression so we can understand what I intend. I mean, until now, probably can understand from here. Look at this expression here, forward Euler. This came from forward Euler. No, let me this one. This is exactly in time. This is exactly in time. No z variable. If I introduce the z variable, we are a little bit disoriented because mathematically it's okay. I defined so as a shifting operator. You understand shifting operator, a shift. But so clear is not. No, shifting, okay. Yeah, absolutely clear. If I show you this, how I can implement this in Simulink, it's extremely easy. U of k, please pay attention, depends of U of k minus 1, but does not depend of U of k. Now, in linear case, no problem. I can realize an explicitization of the expression. But you can see that here, U of k does not depend of U of k minus 1. U of k depends of the previous input. Please pay attention here. No? Here must be U of k minus 1. I cannot accept an E of k plus 1. Because if I write here E of k plus 1, or if I have an E of k plus 1, I have not causal system, not causal. Because it seems that, how possible to say, yeah, that I can have that the output, which is U of k, I would like to formulate so, depends of the future input. Please pay attention. E is the input of the controller. No? This is the present input. This is the past one. I can save in the memory. If I find the file, is easy to understand with the memory, with 1 divided z. It's a shame. In Simulink, we have never tried the same notation, but it's clear that 1 divided z is in the memory. This means shift. I have to build a buffer. How long? In this case, 1 element, because this is the actual element and this is the past one.
Just one step.
Yeah. But if I have somewhere or somehow E of k plus 1, this is the problem, because the output of the controller depends of the future input.
But we don't have.
We don't have. This means or the method is a little bit too abstract, or we have made mistakes in the calculations. Mathematically, I can do whatever I want. It works always. We have already discussed here in the examination, written examination. If I do exactly what the professor presented, 1,0 without, auf Deutsch we say without error. No? But if you want to implement, if here appear A or K plus 1, I don't have the future input. Or we do a model, predictive control, and then there's another, but we need more work, and then we hope that the model is correct. We hope that not happens between the sample time that, okay, this in order to understand what is the meaning between practical. A few minutes, then we take to take a rest to look for the software. But I would like to introduce this. Yeah, explicit, exactly what I told you. What is the difference between explicit and implicit? We can see here, for instance, in the state, x of k is a function of x of k. This is not taught with causality. Causality is something more strange. Here, both are causal, no? Causal. This and this, both. But we can see that on the right part, we have something which depends of k. Here we don't have. This is also allowed because we don't have k plus 1. Not causally means that we have something today, or better to say, roughly speaking, is that the output depends on the future input. This means not causal, not causal. This, of course, mathematically I can do what I want. But then if I want to implement, if I want to look at the physicality, at the feasibility, that cannot be accepted. I cannot do that. I'm not a magician. Here, it's nevertheless causal, but we can see that on the right part, states and input could depend of variable at the same time of the output. Okay. Now, in linear case, we are always able to realize an explicitization of the expression because I can work with algebra, but if S is complex, arcotangent, so not necessarily I can invert the system. Felix, invert the system. This is a little bit the concept. We will see. I don't know if you like this. It's interesting, really. It's a shame in this university we don't have many possibilities. But if I have the possibility, I would like to maintain this course also for the next semester. It's in a Lehrforschung project, not always is fixed to a professor. No? But I don't know if some other professors tell us about it. I don't think so. No? Or at least not in dynamical systems.
I'm not in contact.
Yeah, exactly our case. In the case of controller, we can see that in the here, no? It could happen something like that. Let me see. Yeah, this is the case. This is the case of forward. We can see that the output depends on UK minus 1. In the case of backward, we have this here. This means in order to obtain UK as a function of the input, UK is a function of the E, we must be able to explicit this. But if F is complex, arcotangent over UQ, we cannot obtain UK as the function of the input. Here is already UK as a function of the input because U of K minus 1 could be used as an input. I don't know if it's clear that UK minus 1 is no, it's something which I saved. This I can use for the input. But here, this equation is a little bit embarrassing. I'm disoriented because I need UK, but UK depends on UK selves. And not necessarily is easy to explicit. Of course, in linear case always, because I do some calculation, I bring what I have here in terms of UK on the other part, but this implies that the system is linear. Yeah, this is the explanation about what I told you until now. Okay, let me stop here. Next week, I think we almost conclude about this more theoretical, and then we do more exercise. Let me stop a little bit. If I find in a few minutes the file, the last minutes I show you the file. Otherwise, next week, in order to see a little bit more concretely what happens in the application. In particular, this application 1 divided s squared, which I would like to approximate with the zeta transformation or the discrete form, no? So we can understand better. Okay, let me stop a little bit and then look at the software if I find, and eventually we will restart the last minutes. Okay, I think we can stop here today. Next week I will show you some simulations, then we will go ahead with testing. We complete backward, we do testing, and then Laplace and zeta transform, and then the rest of the course more concrete about controller. At the end, if I have time, I hope, because we have a nevertheless lecture, something about the discrete observer. Huh? So we can apply it, not the Kalman filter, but an Lundberger observer in our project. The Kalman filter is a big topic. Okay, thank you to be here. This means 2 lecture, regular lecture, and then 2 lecture in February, and then we will meet together to perform the project. I will communicate to everybody a little bit the rules about the project. But anyway, the deadline is flexible, and very important to use the MATLAB file which I upload in my study, or speak with me if you have another idea about the representation of the, if you want to use a different tool instead of MATLAB. But I would like to use MATLAB because it's more powerful, and then we need that the students use MATLAB because we have to justify that we buy software for students. Okay, see you next time at the same time here in this room. Thank you to be here today.
Yeah.
Thank you. Bye bye.
Ciao, bye.